Hey y'all, I hope all is well. Today I'm greeting you as Multiple Gavin because we're going to be working on multiple regression. Woo! This is where the true power is at, you guys. So let's start out with a research question that might be asked for multiple regression because it might be a little bit different. You can ask the same type of research questions that we were asking in chapter 14 for simple linear regression as with multiple regression, but we're actually going to open up the world to what a lot of like business analysts, business economists might do, because they might be more interested in a question like the following, which is what are the determinants of house prices? Now let's think about why this is a little bit different than chapter 14. So this is different because there is probably many determinants of house prices, right? Size of house, number of bedrooms, location. So we can sit here and for a long time, we could list the determinants of house prices. Whereas in chapter 14, I might have asked a question like, does house size affect house prices? That's a slightly different question, right? Because I'm picking out one specific thing that I think would affect house prices. But here I'm not picking out a specific thing. I'm saying, hey, I just want to know what all of the things are that affects house prices. So what I would do is start listing them out. What I think would be good to put in what independent variable. So we know our dependent variable, right? That's going to be house prices. But now we might have many independent variables. So one obviously would be house size. So let's put that first in our list of potential independent variables. Another I think would be number of bedrooms. So let's just do two independent variables for now. These are probably both important and just use this to motivate multiple regression. So just like in simple linear regression, we have a population equation. And generally, what a population multiple regression equation will look like is it will have one dependent variable. But now, and then we have an intercept, of course, so beta naught, population intercept unknown. Population slope now beta 1 for our first variable x1. Now notice the only difference so far is I've labeled my first independent variable as x1. Why have I done that? Because now I'm going to keep going. I'm going to put another independent variable in this. So now this equation has two independent variables, x1 and x2. Generally, we can keep going. We could put really as many variables in this equation as we want as long as we have enough data to do that. And then we go plus dot 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 plus beta p for the pth variable. So this is just saying generally I could go up to p variables. That could be 10, 20, 100. When I was an energy analyst, I would be running regressions that had tens to hundreds of independent variables because I had a lot of data. So xp. And then we still have our error term, epsilon. Because even after we're adding more independent variables, we still don't expect it to be a perfect relationship. We don't expect to be able to perfectly guess y with our equation. So to make sure this equality holds, we have to add an error term even in the population equation. So that's a general. That could be the population multiple linear regression equation for any linear regression with up to p variables. Now, specifically for our question, what are the determinants of house prices? And our list of independent variables right here, our population equation would be house price. That's our dependent variable, right? equals beta naught plus beta 1. Now instead of writing x1, I'm going to write house size, because that's my first independent variable in this list right here, right? And then I'm going to write plus beta 2. I'll write it number of beds. So that's my second independent variable, and then plus epsilon because I have an error term. I don't think that house size and number of bedrooms will perfectly explain all house prices. So I think that they won't, that error term accounts for not perfectly explaining them. But I do think that they'll both affect house prices. Okay? So now we can set all this stuff up, this population equation stuff, before we ever look at data. You were implicitly, when you were doing your project, you were thinking about this question, at least one independent variable so far. But now for your final project, you'll start wanting to think about other independent variables. Okay? And so another interpretation of multiple regression would be, well, I really care about the effect, let's say, of number of bedrooms. This is what I care about, okay? But even if you only care about the effect of number of bedrooms, you might want still to add control variables. So many of you will need to add control variables, and this example of house size and number of bedrooms is a really good example. And so let's get into our sample equations, and I'll explain why this can be control variables, I call them, can be really important in these types of regressions. And using house size and number of bedrooms can show how things can change a lot once we include control variables. So 2, we're going to have a sample equation. So now we want to go grab data, right? So for our general one right here, remember, this is our general population equation. Our general sample equation will be y equals b naught plus b1 x1 plus b2 x2 plus dot 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 plus bp xp plus e. So that's just like simple linear regression, except now we have more than one independent variable. All I did was I changed these betas up here, population, intercept, and slopes, to B's, sample, intercept, and sample slopes. I can get my hands on these if I can get my hands on data, right? I can't get my hands on these because I can't get the population data, is what we usually assume. Now for house price and number of beds, I'll get actual numbers. Let's just make some numbers. Let's just make some numbers up. So we could have house price equals, let's say we estimated this, dollars are measured in thousands, or prices are measured in thousands. So we'll say our intercept is 100. So that means that with a lot of land without a house on it is $100,000. That's what that would say if that was the intercept, right? Because that would mean that the house size is 0 and the number of beds are 0. And then let's say we get plus $200 a square foot, maybe. That would be 2. So actually, oops, go away. 0.2, because 0.2 times $1,000 is $200. So I'm just making these up, obviously. But these are something we could get if we went and got data and ran this regression in Excel, right? Now, this is what's going to happen that's going to be crazy about multiple regression. That might seem confusing at first. But I'm going to say minus 2 times number of beds. So that's really weird for now that I would put that number of beds has a negative impact on house price. That's what that says, right? Plus E. Now, I've run a regression with this type of data before, and this tends to actually happen. So what is going on here? Well, what's going on? Let's think about this for a second. Imagine we ran a regression, a simple linear regression, with just one variable, number of beds. And we got 150 plus 3 times number of beds. And we're assuming that I did this with the same data. Would this make sense? So when I run a single regression, I get a positive coefficient on the number of bedrooms. And that makes sense because if we think about the world, what do we observe? Houses with more bedrooms tend to have what? Higher prices. So we'd expect that to be a positive slope. But then what happens is when I add a control variable for size, I get a negative slope. So let's think about what's going on here. When we interpret slopes in multiple regression, we say, so for this -2 right here, I would say, when number of bedrooms increases by 1, house price tends to decrease by $2,000 on average. Holding, oops, I'm sorry, this was a mistake. This should have been house size, right? I put the dependent variable. So this is house size and number of bedrooms. Those are two independent variables based on what I listed up here, right? So sorry, let me start again real quick. If we were interpreting this slope right here, we would say when number of bedrooms increases by 1, house price decreases by $2,000 on average. Why is it 2,000? Because I said prices are measured in thousands of dollars. So when number of bedrooms increases by 1, house price decreases by $2,000, holding house size constant. That's the key difference between these two equations. In this equation, I'm not controlling for house size. So in this equation, I say when number of bedrooms increases by 1, house price increases by $3,000 on average, not holding anything else constant. So in this equation, we're increasing the number of bedrooms without changing the house size. So here we're like adding a bedroom to a small house. What's the only way to do that? Well, the only way to do it is build more walls inside the house. It's totally feasible that that actually causes house prices to decrease because people don't necessarily want 10 bedrooms in a tiny house. In this equation, what we see in the data is that bigger houses tend to have more bedrooms and be more expensive. So we're picking up that effect. But up here, we've controlled for that effect by including house size as a control variable in the equation. So that's a really powerful thing about multiple linear regression. And notice that if our true goal was to determine all of the determinants, we'd want both of those variables at least in that equation. So now this is really important for your project because you're going to go add control variables or additional independent variables, and you might get some unexpected results like this. Or you may have gotten an unexpected result in your draft, and it might be because you didn't control for something important. And that's what this shows, is that things can change a lot when we move into the world of multiple regression, and it's important to think about that. So this was just kind of if we did simple linear regression with one independent variable. So let's talk about a couple things now. So slope interpretation, which I did once, but I'm going to do it again because this is probably the most important thing. Also, one of the places that most people lost points on the draft was just forgetting to do this. And so we need to do that on the final project too, interpret slopes. And so let's just do that again real quick, and I'll write this sentence down. So let's interpret the slope on house size now. When house size increases by 1, house price increases by 200. on average in my data holding number of bedrooms constant. That is the complete interpretation. That's the first interpretation you want to do in multiple regression. So when house size increases by 1, house price increases by $200. That's the slope. It says 0.2 right here. But remember, house price is measured in thousands. 0.2 of 1,000 is 200. That's where that number comes from. When house size increases by 1, house price increases by $200 on average in my data, holding number of bedrooms constant. Notice that is exactly the same slope interpretation we did before with one additional thing. This last phrase right here, holding number of bedrooms constant. Now up here, remember we said you might have a sample equation with like 10 slopes in it, or 10 different independent variables. You don't have to sit here and write holding number of bedrooms, location, and list every single variable constant. You can always say holding other variables, other independent variables constant. So you don't have to list them all out. In this case, if you just have 2, it is good to say holding that other 1 constant, because then it's short. But if you had tons of independent variables, you could always just say holding other independent variables constant. So that's the slope interpretation. The next thing we want to do is find out, are those slopes statistically significant? Because we still have those hypothesis tests sitting in the background. And all of these slopes come from a bell curve, even when we're doing multiple regression. And the way we're going to decide that is to look at the p-values. And if the p-value is less than our level of significance, for example, 5%, 1%, 10%, then we will reject the null hypothesis and we'll say, yes, this slope is statistically significant. I'll go over that, an example of that in the next video, because those will be printed with the Excel results, right? So we can just look at those p-values, look at how big they are. If they are very small, then we'll say, yeah, this is a statistically significant estimate, and there is definitely a linear relationship. If they are big, we will say, no, it doesn't really look like there's a linear relationship between these variables. But that's the same as before. Now 5, we're also going to look at our r squared, or r square. That gets printed in Excel. Now, one thing I want to tell you now is before, when we did simple, well, that's not how you spell simple. It's not simple to spell simple. Linear regression. Our r squared was interpretation, so I'll use the bedroom example right here. If we were interpreting this right here, and let's say we got an r squared of 0.8, number of bedrooms explains 80% of the variation in house prices. Right? So we collect some data and say, look, house prices vary. We know that, right? If I look at a bunch of different houses, the house prices are different. And then I go collect the data on number of bedrooms in all those houses, which also vary, right? And then I run a regression and say, okay, how much of that variation in prices can I explain by variation in number of bedrooms? My r squared tells me the answer to that question, and it's 80%. Now, multiple linear regression. Now we have, let's do this example right here. We have two independent variables, right? So I could say, one way to do this in that example would say house size. So let's say, first of all, one thing I want to point out is that if you start with one independent variable, number of bedrooms, keep that independent variable and add another one, your R squared will always go up. So let's say it went up to 0.9 in this example, okay? So we added house size and our R squared increased. That makes sense because if we add a new variable, we're going to be able to explain more of the variation in house prices. So if I got that for the one where I added size, I'd say house size and number of bedrooms explain 90% of the variation in house prices. Okay? And then of course, if we had 100 independent variables in our determinants of house prices equation, it would be pretty lame to list 100 independent variables in this sentence. So you can always say, my set of independent variables explains 90% of the variation in house prices. With two independent variables, I think it'd probably be better to list them. As you get to 3, 4, 5, it'd probably be better to go in this second interpretation. You can choose. I won't punish you for either. But I just want to mainly point out that when we move from simple linear regression to multiple linear regression, we have a slightly different interpretation of the R squared. We have a slightly different interpretation of slopes. P-values work exactly the same as they did in the last chapter. You just need to look, are they small, big, relative to 1%, 5%, 10%? Same thing we've doing all semester. And this is the only difference here is we're just adding more independent variables. So that's chapter 15. We're not actually doing all of it. Towards the end, they introduce some more complicated models that we're not doing. So you don't even need to do the chapter 15 assignment. So a lot of your focus related to multiple regression really should be working on the project and try to use this video and the next, which is Excel, to get moving forward on the project as soon as you can. All right, so just let me know if you have questions about this, and I will talk to you guys soon.